We had already discussed module 1 of chapter 9. The title of chapter 9 was inner product spaces and Hilbert spaces. Now we shall discuss on module 2 of chapter 9. Module 2 is concerned with geometric aspect, orthogonalization of vectors apart from the length of a vector. We shall discuss on orthogonal vectors, orthonormal vectors and some of its basic results on orthogonal vectors and orthonormal vectors. We are now discussing on module 2. The title of module 2 is orthogonal and orthonormal vectors. Let capital H be a Hilbert space. Let us take a definition. Two elements x and y of capital H are said to be orthogonal if their inner product x comma y is equal to 0, and in symbol we write x perpendicular to y, and sometimes we say x perp y. That means x and y are perpendicular to each other in geometrically. Let capital L be a non-empty subset of a Hilbert space capital H. An element x belonging to capital H is said to be orthogonal to L if inner product x comma y is equal to 0 for all y belonging to capital L. That means x is perpendicular to all elements y in L. That means inner product x comma y is equal to 0 for all y belongs to capital L, and in symbol we write x perp L, that is x is perpendicular to capital L. The set of all elements of capital H which are orthogonal to capital L is called the orthogonal complement of capital L and denoted by L perpendicular. That means the collection of all such elements of H which are orthogonal to capital L. Similarly, we can interpret L perpendicular perpendicular, that is L double perpendicular. Similarly, L triple perpendicular and so on. We write L perpendicular is equal to perpendicular of L perpendicular. Similarly, we get L triple perpendicular and so on. Also, double perpendicular of L perpendicular is equal to perpendicular of L double perpendicular. Two sets capital S1 and capital S2 are said to be orthogonal to each other, written as S1 perpendicular to S2 whenever inner product x comma y is equal to 0 for all x belongs to capital S1 and for all y belongs to capital S2. Let us take a theorem known as Pythagorean theorem. If x comma y belongs to capital H and x perpendicular to y, that is inner product x comma y is equal to 0, then number 1, norm of x plus y whole square is equal to norm x square plus norm y square, and number 2, norm x minus y whole square is equal to norm x square plus norm y square. Since x perpendicular to y, inner product x comma y equal to 0. So, number 1, norm of x plus y whole square is equal to inner product x plus y comma x plus y, and by the inner product property, that is inner product axiom 3, we get inner product x plus y comma x plus y is equal to x comma x plus x comma y plus y comma x plus y comma y, which is equals to inner product x comma x plus y comma y, because inner product x comma y equal to 0. Since inner product x comma y equal to 0, we get inner product y comma x is equal to 0. Thus, norm of x plus y whole square is equal to inner product x comma x plus inner product y comma y, which is again equals to norm of x square plus norm of y square. And number 2, norm of x minus y whole square is equal to inner product x minus y comma x minus y, which on inner product axiom IP3 we get inner product x comma x minus x comma y minus y comma x plus y comma y, which is again equals to inner product x comma x plus inner product y comma y, because inner product x comma y is equal to 0 and inner product y comma x is equal to 0 as x is perpendicular to y. So, inner product x comma x plus inner product y comma y is equal to norm of x square plus norm of y square. Thus, norm of x plus y whole square is equal to norm x square plus norm y square, and norm of x minus y whole square is equal to norm of x square plus norm of y square due to x perpendicular to y. Let capital S be a subset of a Hilbert space H, then perpendicular of singleton 0 vector is equal to H and perpendicular of H is equal to singleton vector 0 vector. Number 2, if capital S be a subspace of capital H, then S meet S perp is equal to singleton 0 vector, that is theta vector. Number 3, if S1 is a subset of S2 which is a subset of capital H, then S1 perpendicular includes S2 perpendicular. Number 4, S is a subset of S double perpendicular. Number 5, perpendicular of S double perpendicular is equal to S perpendicular. Number 6, if capital S is a subset of H, then S perpendicular is a closed subspace of capital H. The proofs of 1 and 2 are very trivial and so left out. For 3, let us take a proof. Let x belongs to S2 perpendicular. So, inner product x comma y is equal to 0 for all y belongs to S2. So, inner product y comma x is equal to 0 for all y belongs to S2. This implies y comma x is equal to 0 for all y belongs to S1, as S1 is a subset of S2. So, x belongs to S1 perpendicular. Hence, S2 perpendicular is a subset of S1 perpendicular, because we have started with an element x belonging to S2 perpendicular and we have seen that x belongs to S1 perpendicular. For the proof of 4, let us take an element x belonging to capital S. Then inner product y comma x is equal to 0 for all y belongs to S perpendicular. So, x belongs to perpendicular of S perpendicular. Thus, S is a subset of perpendicular of S perpendicular, which is equal to S double perpendicular. For the proof of 5, by 4 we have seen S is a subset of S double perpendicular. So, by 3, perpendicular of S double perpendicular is a subset of S perpendicular. Again by 4, S perpendicular subset of double perpendicular of S perpendicular, which is equal to perpendicular of S double perpendicular. Hence, S perpendicular is equal to perpendicular of S double perpendicular. For 6, let us take x comma y belonging to S perpendicular and alpha be any complex scalar. Therefore, x is perpendicular to S and y is perpendicular to S. That means, x minus y belongs to perpendicular to S and alpha x perpendicular to S, because x minus y is perpendicular to S. So, x minus y and alpha x belongs to S perpendicular, because alpha x is perpendicular to capital S. Consequently, S perpendicular is a linear subspace of capital H. We shall now show that S perpendicular is closed. For this, we shall show that S perpendicular bar is equal to S perpendicular. For this, we start with an element x belonging to S perpendicular bar. So, there exists a sequence of elements xk in S such that limit k of xk is equal to x with xk is perpendicular to S. as xk is perpendicular to capital S, inner product xk comma y for all y belongs to x is equal to 0. Also we have seen that limit k xk is equal to x. By the continuity of inner product we see that x is perpendicular to y for all y belongs to capital S. Thus we see that x is perpendicular to S, that means x belongs to S perpendicular, and consequently S perpendicular bar is a subset of S perpendicular. It is obvious that S perpendicular is a subset of S perpendicular bar, that means S perpendicular is equal to S perpendicular bar, and hence S perpendicular is closed. Now in this connection let us take a theorem. In an inner product space capital X, number 1, if a vector x belonging to capital X is orthogonal to a subset capital A of capital X, then X is orthogonal to the linear hull of capital A. Number 2, if a vector x belonging to capital X is orthogonal to an infinite sequence yk, where k equal to 1, 2 and so on in capital X, and limit yn is equal to y0, then x is perpendicular to y0 where y0 belongs to capital X. Number 3, if capital A be a dense subset of capital X and if x belongs to capital X be orthogonal to A, then x must be equal to 0 vector, that is x is equal to theta. We shall prove one by one. For the proof of 1, let y1, y2 dot dot yn be a finite subset of capital A. Therefore, x is perpendicular to yk for k equal to 1, 2 and so on. This implies that x perpendicular to beta 1 y1 plus beta 2 y2 plus dot 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 plus beta n yn for arbitrary scalars beta 1, beta 2, beta n. Because if we take an inner product x comma beta 1 y1 plus beta 2 y2 plus dot 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 plus beta n yn, we get inner product x comma beta 1 y1 plus beta 2 y2 plus dot 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 plus beta n yn is equal to beta 1 bar inner product x comma y1 plus beta 2 bar inner product x comma y2 plus beta n bar inner product x comma yn. As inner product x comma yk is equal to 0 for k equal to 1, 2 up to n, we see that beta 1 bar inner product x comma y1 is equal to 0, beta 2 bar inner product x comma y2 is equal to 0, dot 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 beta n bar inner product x comma yn is equal to 0, and consequently x is perpendicular to beta 1 y1 plus beta 2 y2 plus dot 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 plus beta n yn for arbitrary scalars beta 1, beta 2 dot dot beta n, but the scalars are finite. Since inner product x comma beta 1 y1 plus beta 2 y2 plus dot 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 plus beta n yn is equal to sigma k equal to 1 to n beta k bar inner product x comma yk is equal to 0, as inner product x comma yk is equal to 0 for each k equal to 1 to up to so n, it follows that x is orthogonal to the linear hull of capital A. For the proof of 2, modulus of inner product x comma y0 is equal to modulus of inner product x comma y0 minus inner product x comma yn, because x is perpendicular to yk for k equal to 1, 2 and so on. So, modulus of inner product x comma y0 minus inner product of x comma yn is equal to modulus of inner product x comma y0 minus yn by inner product axiom IP3, which is again less or equals to norm x into norm of y0 minus yn. This follows due to the Cauchy-Schwarz inequality. As norm of y0 minus yn tends to 0 as n tends to infinity, so modulus of inner product x comma y0 is equal to 0, and hence x is perpendicular to y0. For the proof of 3, let z be an arbitrary elements of capital X. Since capital A is a dense subset of capital X, there exists a sequence of elements yk, k equal to 1, 2 and so on in capital X, such that limit yn is equal to z, limit is taken over n. Since x is perpendicular to yk for k equal to 1, 2 and so on, we get x is perpendicular to z by the continuity of inner product. Thus, inner product x comma z is equal to 0 for every z belongs to capital X. In particular, inner product x comma x is equal to 0, so x must be equal to theta, that is x is equal to 0 vector. Now, let us take a definition. A non-empty set EI of a Hilbert space capital H is said to be an orthonormal system if number 1, inner product EI Ej equal to 0 for I not equal to j, and number 2, norm of EI is equal to 1 for every I. That is, any vector of the system is non-zero unit vector in capital H. Number B, if an orthonormal system of capital H is countable, then we can enumerate its element in a sequence and then we say it is an orthonormal sequence. Let us take an example. In Rn or Cn, that is n dimensional Euclidean space over the field of reals or n dimensional Euclidean space over the field of complex scalars, the orthonormal set of vectors are of the type 0, 0, 0, 1, 1 is taken in the kth place, comma 0, 0, 0 and denoted by Ek. Clearly, norm of Ek is equal to 1 and inner product Ei Ej equal to 0 for I not is equal to j by easy calculation. Let us take another example. Let capital L2 0 2 pi, it is a function space, that is L2 0 2 pi be the real Hilbert space of all square integrable functions over 0 to 2 pi, and the functions must be measurable and integration 0 to 2 pi f square dt exists. Define an inner product on x by inner product x comma y is equal to integration 0 to 2 pi xt into yt dt, where x and y are taken from L2 0 2 pi. So, norm of x square is equal to integration 0 to 2 pi mod of xt square dt, where x belongs to L2 0 2 pi. Let E0t is equal to 1 by root over 2 pi, ENT equal to cos nt by root over pi, n equal to 1, 2 and so on, and t belongs to 0 to 2 pi. Then E0 and set En forms an orthonormal set, because by reduction formula we see that integration 0 to 2 pi cos mt cos nt dt equal to 0 if m not equal to n, integration 0 to 2 pi cos mt cos nt dt is equal to pi if m is equal to n is equal to 1, 2 and so on, integration 0 to 2 pi cos mt cos nt dt equal to 2 pi if m is equal to n is equal to 0. Now, we take a theorem that every finite dimensional inner product space is complete and is therefore a Hilbert space. The proof goes below. Let capital X be an inner product space over a field of complex scalars and capital X is of finite dimension, say equal to n. Then there exists a basis of capital X formed by a orthonormal set of vectors x1, x2 dot dot xn, because we see that orthonormal set of vectors are linearly independent. So, any vector x belongs to capital X can be expressed as x is equal to zeta 1 x1 plus zeta 2 x2 plus dot dot zeta n xn for some scalars zeta 1 zeta 2 dot dot zeta n, and norm of x square is equal to inner product x comma x, and substitute x for zeta 1 x1 plus zeta 2 x2 plus dot 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 zeta n xn. So, we get norm of x square is equal to inner product zeta 1 x1 plus zeta 2 x2 plus dot dot plus zeta n xn, comma zeta 1 x1 plus zeta 2 x2 plus dot 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 plus zeta n xn, which is again equals to modulus of zeta 1 square plus modulus of zeta 2 square plus dot 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 plus modulus of zeta n square, since inner product xr comma xs is equal to 0 if r not equal to s, inner product xr comma xs is equal to 1 if r equal to s. We shall now show that this is complete. So, we start with a Cauchy sequence. Let yk be a Cauchy sequence in capital X and let yk equal to beta k1 x1 plus beta k2 x2 plus beta kn xn for k equal to 1 to up to n for some scalars beta k1, beta k2 up to beta kn, and x1, x2, xn are the linearly independent set of vectors in capital X. Therefore, norm of yr minus ys square is equal to inner product yr minus ys comma yr minus ys, which is equals to inner product beta r1 minus beta s1 into x1 plus beta r2 minus beta s2 into x2 plus plus beta rn minus beta sn into xn comma beta r1 minus beta s1 into x1 plus beta r2 minus beta s2 into x2 plus plus beta rn minus beta sn into xn, which is equal to modulus of beta r1 minus beta s1 square plus beta r2 minus beta s2 square plus plus beta rn minus beta sn square, which goes to 0 as r comma s tends to infinity. This implies that modulus of beta rj minus beta sj tends to 0 as r comma s tends to infinity for j equal to 1 to up to n. Hence, the sequence beta kj where k equal to 1 to and so on and j equal to 1 to up to n is a Cauchy sequence in C. And since scalar field C is complete, sequence beta kj is also convergent in C for j equal to 1 to and so on. Let limit k beta kj equal to beta j for j equal to 1 2 and so on, and let us take y equal to beta 1 x1 plus beta 2 x2 plus beta n xn for some scalars beta 1 beta 2 beta n, where beta j equal to limit k beta kj. So, norm of yk minus y square is equal to modulus of beta k1 minus beta 1 square plus plus beta kn minus beta n square, which goes to 0 as k tends to infinity for j equal to 1 to up to n. Consequently, limit k of yk is equal to y. Thus, the Cauchy sequence yk where k equal to 1 to and so on converges to an element y belonging to capital X, and so X becomes a Hilbert space. If capital M and capital N are two closed subspaces of a Hilbert space H with M perpendicular to N, then M plus N is always closed in capital H. The proof is very simple, and so it is left out. Up to this, we have defined when two vectors are orthogonal, when is a vector is an orthonormal vector. In this connection, we have got a theorem known as Pythagorean theorem. That means, if x is perpendicular to y, then norm of x plus y whole square is equal to norm of x square plus norm of y square. Similarly, norm of x minus y whole square is equal to norm of x square plus norm of y square. Also, we have learned when a vector x is perpendicular to a subset S of capital X. Also, we have a property on a vector x and a subset of S in connection with the orthogonality and orthonormality. In this module, we have learned orthogonal vectors, orthonormal vectors, and some properties on orthogonal vectors and orthonormal vectors. Also, we have proved a result that any orthonormal set of vectors is linearly independent in a Hilbert space H, and any finite dimensional inner product space is complete. With this, we now come to an end of this module.